Okay. Okay, so the second presenter is Professor Yu-Chen and Dr. Chen. So Professor Yu-Chen, he got the master degree and PhD degree from the Electronic and Computer Engineering from the National Taiwan University of Science and Technology in Taiwan in 2009 and 2015 respectively. And he was a business researcher in the FEC lab in Virginia Tech, Blacksburg in 2014. And he was the research assistant professor in the NTUST from 2015 to 2016. And he's currently the associate professor with the Department of Electrical Engineering in the National Ilan University, Taiwan. And he earned the Young Researcher Award in 2018 from the National Science Council of Taiwan. And he serves as a faculty advisor for student teams for IEEE International Future Energy Challenge, IFEC, in several years from 2015 to 2019, and he got several awards. And he also the chair of the IEEE Industrial Applications Society Taipei Chapter from 2017 and 2018. And his research interests include the analysis and design of the DC-DC converter, power factor correction, and high frequency converter design. And today come with him is Dr. Chen. He will present with Professor Yu-Chen. And Dr. Chen also got the master degree and PhD degree from National Taiwan University of Science and Technology. And he was the business researcher at the Center of Power Electronic Systems, CPES, in Virginia Tech from 2019 to 2020. And his research interests include the analysis and design of the DC-DC converter, wide bandgap device application, high frequency controller implementation, and the design of magnetic in high frequency application. So today's topics of is the high frequency transformer design for the high power density converter. So let's welcome Professor Yu-Chen and Dr. Chen.
Okay, thanks for Yong's introduction, Dr. Yong's introduction. So today, me and Dr. Chen will going to present the high frequency transformer design for high power density converters. It's our great pleasure to share our experimental result in a few past year about the high power density converters. So can you see my screen?
Yes, very well.
Okay, so I'll keep going. So yeah, so this part is just like Dr. Young's introduced, so I will pass very fast. Actually, in this slide, all the research result is based on the two laboratory. One is from the National Taiwan University of Science and Technology, and the other is from National Ilan University. So I'm today's presenter, Stephen. You can just call me Stephen. And this is another presenter, Chen. Okay, so before we start this presentation, I want to do some acknowledgement. So all the if you are interested in more detail, we list the reference as the button, so you can find more detail in the reference we said that. And the others, I want to emphasize the Dr. Huangren Qiu from Taiwan Tech and Dr. Catherine Kim from NTU, and without their help, this I cannot make it. So I would like to express my great appreciation to my PhD student and the master student. Okay. So here's our outline today. We'll introduce the high frequency converter design and high frequency magnetic component design, and we will give you some example. So just like a professor in the last hour, the professor mentioned about the future is about the high efficiency converter. So we will talk about of course, we will talk about the background and talk about how to implement the high performance and high efficiency converters. Okay, so here's the background. So everyone uses a mobile phone. So right now we know the computing time is quite a challenge for everyone need more a fast computing for your cell phone, right? So the data center power supply requirement is increased year by year. So if we can like improve the conversion efficiency, that means we can like save a lot of energy. So in this slide shows if we can improve 1% efficiency, then we can save like 3 nuclear power plants. So that is very huge effect. Okay, so next page. So here's the conventional server power supply design. So usually we'll operate it in 100 kilohertz, and conventional efficiency is like a 96%. The power density is just like this value. So we have a 2-stage, but because the switching frequency is lower, so we cannot like reduce the circuit volume. So the idea is based on this same power level, we want to reduce the volume. So the only way we want to reduce the volume is increase the switching frequency, because when we increase the switching frequency, we can reduce the volume of the path components. But the target is we still want to keep the same conversion efficiency. It's not like we increase the switching frequency and the conversion efficiency is lower than before. So we don't want to do that. So that is our target. So just like Professor mentioned before, we have a new devices, wide bandgap device. It can have a better characteristic, can help us to reduce the switching loss, but that is not enough to make this goal, to achieve this goal. Okay. So for the power converter design factors, we have a few parts. We'll say the magnetics, switching, driver, and loss and heat control and EMI. They are very big topic in this area. Okay, so if we want to design a high frequency magnetics, there are few people. There are a lot of people focus on the material and how about magnetic structures. And for the switching devices, we will use the wide bandgap switching devices like gallium nitride and silicon carbide. They have no reverse recovery. They have a fast switching speed. And we need to design a special driver for the wide bandgap devices. And the other is loss and heat control and EMI. So here are some like a wide bandgap switching company. Actually, we have more company. They are doing the wide bandgap devices right now. Okay. So here's we have a lower RDS-on and higher switching speed. So the challenge with the high switching frequency converter, the first one is you need to know how to drive the wide bandgap devices. So everyone, that is the best requirement. And the next one is if you want like reduce the volume, you want to save the volume, then you need to increase the switching frequency. That means you will get a smaller magnetics or capacitor. So because you increase the switching frequency, and you should have like how to stop the loss and heat, and how to do a control for the high frequency, how to stop the EMI in a high frequency condition. So that is a challenge. Okay, so before some people like a professor they just mentioned, like I can operate it in a low frequency and using a wide bandgap devices, so I still can gain the benefits from at this condition. The reason is we have very fast switching speed for these new devices. Okay, so we will analysis on the background about the switching loss. So here are two equations. One is for the turn-on switching loss, the other is for the turn-off switching loss. As we know, even we have a very fast switching devices, like we will have a small like rising time and falling time, but the switching loss is still depend on the switching frequency. So if we increase the switching frequency to a megahertz, that means the switching loss will also increase too. Okay, so that is kind of like a trade-off part. So the most important thing, if we want to achieve the high frequency converter, we need to think about, can we achieve the zero voltage switching or zero current switching for our control? Okay, so for the conventional design, there's a 4-bridge phase shift and resonant converter are proposed for the commercial power supply design. Here's a 4-bridge phase shift. The advantage of this topology is like we have an output inductor, so the output ripple will be very small. But for the primary side, the leak index cannot achieve the 0 voltage switching at a light load condition. So that means if we use this topology operating at a very high frequency, that means we still have the higher switching loss. And the other topology is most of people use this right now is a resonant converter. We can achieve the DVS in the entire load condition. And but the disadvantage is like the output we doesn't have the output inductor, so the output ripple will be very will higher than the full bridge phase shift one. But we can have a DVS if we operate in the LLC region. We can have a DVS at the primary side and the DCS at the secondary side. Okay. So here's the resonant converter. The benefit of the LLC region is the voltage gain is equal to 1. So usually when we design a high efficiency, high power density resonant converter, usually there's a name we call the DC chart. That means we only operate it in the resonant point and can get the maximum efficiency. Okay, so I want to use this example to present how to do the megahertz resonant converter. So here is a conventional design for the 100 kilohertz LLC converter. The input is 380 volt and output is 12 volt and output power is 1 kilowatt. So I just use the conventional silicon devices to implement the circuit. Okay, so as you can see, we use a very large transformer for this design. Okay, so here's a loss breakdown. As you can see, the secondary side is got the highest loss here. Okay, so in the primary side, because the transformer, we use the least wire to make our transformer and use the PCB widening to be our secondary side. And the secondary synchronous rectifier, we use the silicon devices. Okay, so if we want increase the frequency to a 1 megahertz and we doesn't change anything, then we will see what happened. So if we increase the switching frequency to a 1 megahertz, the advantage is we can reduce the transformer size. And we can also use the leakage inductance to be a resonant inductor. So that means I don't need the extra resonant inductor. I can use the transformer's own like a leakage inductor to be our resonant inductor. So I can like take out the resonant inductor here. But the disadvantage is because I still use the material, the core material for the low frequency. So the core loss and the switching loss will be increased. So here's what I did. So I just increased the frequency to a 1 megahertz. So as I told before, the core loss will be increased because we still use the wrong material, and switching loss is also increased because we still use the silicon devices. So the turn off time and turn on time. The turn on part is we have a DVS. So the turn on loss is still very small, but the turn off loss is increased. Okay. So compared with the 1 megahertz and 100 kilohertz, we can see the core loss is increased 37.65 watt. So that is a huge difference. The switching loss is increased 2.05 watt. The number is only 2.05 watt because the switching loss, the LLC has a turn on DVS. So if we increase the switching frequency to a 1 megahertz, that means the turn on loss will be minor. Okay, but the turn off loss will be increased. Okay, so the other is the driving loss. So here's here's a picture very interesting. I find it from the internet. So here's like a Superman, is GaN, there's a silicon carbide. So even we have like these new devices can operate in very high frequency. They have very good characteristics like for high frequency control. But the most important part is if we cannot design the magnetics very well, that means we cannot get a very good performance for the high frequency application. So I will do some summarize for the 1 megahertz resonant converter. Like if we want to do the high frequency resonant converter, I will say the core loss increase with the switching frequency. So the core material it should be for the high frequency application should be unitized. That means we need to find the right material for the design. And in the high frequency design, the AC resistance, it will be a major like a AC resistor loss. So how to make the AC resistance lower than before, that is another very serious topic in the high frequency design. So it's a little bit different when you design a low frequency converter. When you design a high frequency converter, you need to be very careful about all the detailed design in a transformer or your driving loop, okay? Because the physics phenomenon for this kind of like high frequency based on this high frequency condition. Okay, so next part I will move to Dr. Chen. He will talk about some like high frequency magnetic components design.
Hi everyone, I'm Chen. This part is talking about high frequency magnetic component design. For transformer loads, it can be divided to two parts: the core loads, copper loads, and okay. So we should consider core material AC flux density and frequency when do the core loads design, and consider copper thickness, NF, air gap, and the frequency when do the copper loads design. Different core material have different hysteresis loops. For soft ferrite material, row remainers easy to demagnetize and small Birch curve area. And it is suitable for high frequency switching converter design. Okay. And AC flux density can be determined using Faraday's law. Different transformer voltage waveform will produce different flux waveforms. So Faraday's law can be used to get the requirement maximum flux density. Okay. By CPES core loss measurement result, ML91 from Hitachi has the lowest core loss performance at 1 MHz, and DMR51W from DMEGC has the lowest core loss at 500 kHz. Okay. In conventional design, we generally choose Bmax at half bit saturation. So as you can see, PCB at 1 MHz will be much higher than 100 kHz. Based on this calculation, Bmax should be designed to be less than 1000 Gauss at high frequency operation. So it is difficult to measure the core loss accurately. So we will use a Maxwell and Simplorier to co-simulate the core loss. Okay, so next we will introduce the copper loss. The copper loss can be divided into two parts. One is DC resistance, another is AC resistance. Okay, so DC resistance related to cross-section area and conductor length. Increasing cross-section area or reducing length reduce DC copper loss. So for the first equation, the calculation is simple, but as the frequency increases, the calculation error will increase. So for the second equation, the calculation is complicated, but the calculation result is more accurate. Okay. For this page, engineers usually use a PCB trace calculator to design a PCB winding, and you can get the result after you input these data. But there is no function for frequency from this calculator, so it didn't consider AC copper loss, and it will impact copper loss a lot at high frequencies. Okay, so we will introduce the eddy current. The eddy current is the most important to calculate copper loss. So when current through a transformer winding generate a changing magnetic field, according to Faraday's law, these magnetic fields generate an electromagnetic force in the conductor that create eddy current. This eddy current causes conductor loss and generate heat. So first, the skin effect for the copper loss. The AC current through the conductor generate eddy currents, and the eddy current induce a current in the upside direction as the original current. So as you can see, the total current through the conductor is the same, but the effect cross-section area is reduced. So the current density increases and the loss increases. Okay, skin depths can be derived from Maxwell equation. There are two different skin depth values from dielectric conductor and normal conductor. For the same copper wire, AC resistance increases over 4 times from 100 kHz to 1 MHz. If the frequency keep increasing to 4 MHz, the AC resistance will increase over 8 times. So this page shows a skin effect simulation result using Maxwell. When the frequency operates at low 6 kHz or 60 kHz, the copper loss is closing to each other. But the frequency increases to 600 kHz. Copper loss of the lead wire will be 2 times higher than PCB winding trace. This page shows a proximity effect of copper loss. The difference between skin effect and proximity effect. Skin effect is due to eddy currents caused by its own magnetic field, but the proximity effect is due to eddy current in a neighboring conductor. So when the current flows through the conductor and the eddy current are caused by both the skin effect and proximity effect. When no current flows through to the conductor, eddy currents are only caused by the proximity effect. But the transformers are constructed with multiple windings, so the proximity effect is more critical. Loss caused by the proximity can be explained by the NF. The higher NF, the larger proximity effect and higher impact of eddy current. Winding method effect in NF. For non-interleaving winding at 100 kHz, the maximum NF point costs 1.26 times RDC. When the frequency increases to 1 MHz, the RDC will increase to 22 times at the same maximum NF point. From figure at right-hand side, when frequency increases, the proximity effect increases. If a switching frequency is determined by converters, how to optimize winding arrangement to reduce proximity effect is very important things for copper loss. Interleaf winding is effective to reduce NF to get lower copper loss. This page shows proximity effect simulation using Maxwell. The circle one and the rectangular one represent primary winding and secondary winding respectively. First case is a non-interleaf winding. The copper loss of 1 MHz is 3 times higher than 100 kHz. The second case is partial interleaf windings. The copper loss of 1 MHz is still 3 times higher than 100 kHz, but the copper loss is much lower than the non-interleaf windings. Third case is fully interleaf windings. The copper loss of 1 MHz is around 2 times higher than 100 kHz. Losses for each winding structure are summarized below. AC resistance is much higher at higher frequencies than lower frequencies. For transformer windings, if completing interleaving is not possible, partial interleaving can still greatly reduce copper loss at 1 MHz and higher. Complete interleaving is most effective to reduce overall copper loss. In transformer applications, an air gap can be added to reduce the attenuation of the inductance caused by high DC bias. However, increasing the air gap also increases leakage flux. The leakage flux through the conductor can cause the eddy current to generate hot spots and further losses. This page shows the fringing effect simulation using Maxwell. The first case is using this wire. Adding an air gap at any location increases losses by 2.5 to 3.7 times. The second case is using PCB windings. Adding a gap at any location increases loss by 1.6 to 2.58 times. Compared to this wire, the PCB winding are less effective by the fringing effect. So next we will introduce the winding comparison. For high power density applications, winding space is limited. For the same transformer window area, PCB traces have a smaller DC resistance. Thus, PCB traces are used instead of this wire for high frequency applications. For conventional PCB traces, trace width is generally constant over the length. An advantage of PCB trace over this wire is that the trace width can be adjusted. Increasing the PCB of the outer loop trace can reduce overall RDC. Okay, so this page is introducing these PCB winding optimization skills. R1 is inner ring resistance, and R2 is outer ring resistance. X is the radius of the inner and the outer winding separation. Suppose R1 equal to R2, then R1 plus R2 will be at its minimum value, and the core can be wound to get the best efficiency. So we can find the X value after differential. The X value equals to root outside radius capital R and inner radius R. However, this X value is ideal because the actual distance between the windings need to be considered. A correction terms need to be added. So W equals to A plus B, and B's value is shown as below. And we will give an example to explain how it works. The gap between two windings is 0.5 millimeter. The result shows R1 will equals to R2 after adding correction term. So it is important to design for reduced core and copper loss under high frequency application. For core loss, you have to consider hysteresis loss and eddy current loss. For copper loss, you can reduce DC copper loss by winding optimization. For AC copper loss, choose an appropriate conductor thickness. Reduce loss with interleaving windings. Choose a proper air gap position and winding shape to reduce losses.
Okay. So thanks for Dr. Chen. I'm Steven. So I will going to talk about some design example for the panel transformer design. Okay. So first we'll talk about this is the paper we already published in last year. It's called a quarter turns fractional turns transformer, and this one is a quarter turn design. So as we know, so when you design the resonant converters, the turns ratio is fixed. For example, if we want to design a 300 volt input voltage and output is a 12 volt, the turns ratio usually is 16:1. So that means the secondary side, however, even though you increase the frequency to a 10 megahertz, the turns ratio still fixed to 16:1. So that means even you increase the frequency a lot, but you still cannot reduce the turns ratio. Okay, so some professors' idea is about like a fractional turns, like I can make the turns to the half turns or the quarter turns. So the professor from Kunming, he proposed an idea about a half turn design, and we based on that idea to design a quarter turns transformers. So as you can see, this figure we shows the idea is like we try to talk about a different turns ratio, like a 1/2, 1/3, and 1/4 turns. And we can see compared with the total loss with this like comparison condition, the 1/4 we call the quarter turns, we can get a best performance, like a lower total loss. Okay, so here's the specification and the turns ratio. So the actual turns ratio is 4 to 0.25. So the figure one shows the architecture of the proposed fractional turns resonant converter. The operation frequency was fixed at the resonant frequency to achieve the maximum efficiency for a resonant converter. And the other figure shows the primary side winding. It has 4 turns around the central leg, and the secondary side winding each secondary side winding have a 0.5 of the turns. Okay. So during the positive period, the primary side high side switching S1 is on and the low side switching S2 is off, just like this figure shows. And the primary side current flows in a clockwise direction, including the magnetic field into the core. According to the Friday's law, the secondary side of the transformer generated a clockwise current to the receive the change in magnetic field such that the secondary side current flows from GND through the synchronous rectifier A and the secondary side winding to a VL. The VL in the figures are all the same voltage node and the ground point are all the same ground. Okay, so the 4 secondary side output winding are in the parallel and the equivalent number of the turns is 0.25, like a quarter turns. Okay. So this is the same like a positive cycle. So we also consider about how to design the different PCB layer to make it interleave to reduce the AC loss. Okay. So it's very hard to based on the mathematic calculation to get the core loss and the couple loss. So in our research center, we just based on the simulation software like Maxwell. We can use the Maxwell to help us to analyze the core loss and the flux distribution to make sure when we design the core, it won't get a CPES in our operation. When we do when circuits work, the core will not CPES. Okay, so we also use the Q3D software to make sure the loop inductance and loop resistance to make sure the current is sharing is not like there's or the some corner has a higher loss density, then we can based on this simulation try to avoid to improve this kind of effect and try to reduce the loss. Okay, and we also use the Maxwell to verify, because when we design this kind of planar transformer, usually in this case it's like 12 layers. So if we got a PCB and the output is wrong, the first one is very expensive. So before we make the PCB, we will use the Maxwell to verify the input voltage and the output voltage is correct or not. So we will use the Maxwell to help us to understand each set of central tap current is equal. Okay, so here's our design for the quarter turns. So of course we use the GaN device at the primary side, and we use our quarter turns transformer. Okay, so this is a top view, and the other is the bottom one is for the bottom view. Okay, so here's our efficiency. The peak efficiency is 97.01, and we use the GaN devices for primary side, and the core material is a 3F46. It's for the megahertz design. Okay, so compare with the conventional like 100 kilohertz and the matrix transformer from the CPES and our proposed magnetic structure, we can see that some advantages like for a low frequency one, actually it's very easier to control. For the control is kind of easier compared with the high frequency one. But if we want reduce the volume, the low frequency is very hard because the magnetic is operated in low frequency, so we cannot reduce the magnetics size. And for the CPES idea, they have like their advantages. They have a higher power density, and the core loss because they have a flux cancellation, so we can reduce the core loss. But the disadvantage is about the secondary side still turns is still equals to 1. So we have the conduction loss will be higher than quarter turns. So the quarter turns, the disadvantage is because the primary size turns is lower, it's become like a 4 to 0.25, right? So that means we need to use a large transformer to keep the same flux density. So that is kind of a disadvantage. Like we need to use a large code to achieve the quarter turns idea. But this advantage is like the secondary side loss will be reduced compared with the one turns. Okay, so here's some research topic we did already did in these 2 years. So one is for this is a 1 megahertz resonant converter. It's also the DC application. The efficiency is 97. And sorry. So this is another idea. Sorry, novel half-turns transformer. In this idea, which we just write a paper and it's still in the review process. And the main concept is we will try to solve the problem like the quarter turns we cannot reduce because the primary side widening is very small, so we cannot reduce the core size. But in this novel half turns idea, like we can reduce the core size. Okay, so here's the result we have. Okay, so we can increase the power density to like 55 central cube per watt. Okay, so this is another topic, just like the professor just talked about. It's a low frequency one, low voltage one is a 48 volt to 6 volt. The peak is still use the quarter turns. The frequency is 1 megahertz. The peak efficiency is 98.2. And compare with the other research center, we can get a very high efficiency because the quarter turn can make especially in the higher current design, we want the loop, the PCB current loop as small as possible. So when we use this like a transformer structure, we can reduce the copper loss in either primary side and the secondary side. Okay, so here's another concept about high frequency control, but we only use the like 3 pages. But if you are interested in, we also published a paper for this idea. Okay, so this is not a new idea. Actually, this idea is from the CPES, Virginia Tech. So their idea is like we have a UI code right now, and the primary widening and secondary widening are symmetric. Okay, so as you can see, the flux is the same for each deck. Okay, the leakage inductance and the resonant, the magnetizing inductance and resonant inductance value are as below. So here's the EI code. So if we can do some like a little bit like a change about the widening to make the flux is different for each deck, so that is a total fine. So because the widening is different at each deck, so we will have an extra flux go through a central tab. So that means if we can control the width of the central leg, that means we can control the leakage inductor. So here's the simulation result. So we just did a different like central leg width. So based on the different central leg width, we can get the different leakage inductors. So here's a table. We can see width of the central leg from 0.1 millimeter to 1 millimeter. We can get a higher. If the width of the central leg is larger, so we can get a higher leakage inductors. So that is how we do the controllable leakage inductor. Okay, so here's our design. Actually, we have like a 2 paper talk about this circuit. Is a on-board charger with an integrated magnetic design. So in the front, this is a CLC circuit. So we just integrate to like a resonant inductor. So this is a conventional circuit. We will have 3 magnetic components, but based on this proposed idea, we can integrate into one. Okay, and because the code shape we design is a circle, is a round, so we can reduce the conductive path. Okay. So I will going to give the summarize of this talk. We discuss about high frequency operation. So as we know, compared with the low frequency operation, and the design concept is really different. So it's not just use the new GaN devices like right now. It's we have so many documents talk about how to use the wide bandgap devices, but the most important thing is if you want to increase the efficiency, it's not just about like a change or replace the power devices. Okay, so the next step is if you want to achieve the higher performance, you need to know the passive component is quite important for your design. And how to design a high frequency converter, you need to consider about so many different parts. Like when you design the layout, you should be very careful about the layout loop. You need to try to reduce all the parasitic parameters in your layout loop. And when you design the passive component, is also quite important because you cannot use the old material to design a high frequency switching power supply. So there's so many different things we need to like very careful to design. Okay, and if you want to do a research, I mean, it's a very interested idea in the near future. So many people, they are focused on very high power density, high efficiency design. So I will give you some conclusion like this is a very interesting topic in the future, and still have so many people are focused on how to development a new material for the passive components, or you can try to think about how to design a new transformer structure to reduce the couple loss or the core loss. And here we give you some example about a fractional turns transformer for the high frequency design, but this is just one of the idea for the high frequency application. They still have a lot of like a different design center. They propose a very good idea for in this field. Okay, so to achieve the high performance and high power density converter, we should find suitable switches and the core material. Okay, and different transformer structure are used to reduce the power loss and the high frequency and high power density. So yeah, so thank you everyone. So maybe we'll open for a few questions.
Okay. Yeah, thank you very much for your very nice presentation. And you gave us a very good guideline for design of the planar transformer, and also give us a lot of novelty on the power converter application. And there are a lot of questions. Yeah, I think so. So firstly, I would like to ask like Dr. Nguyen. Yeah, is the first one to ask questions.
Okay, thank you very much. This is Gwen from Japan. I'm now doing postdoctoral in Japan in terms of electronics as well.
Hello.
Thank you very much for your very nice presentation. I have not a couple, but 4 questions totally.
Okay.
Sorry. The first one, at the beginning of your presentation, you said that at the high frequency, I mean, in the order of 1 megahertz, you said that ferrite is not suitable material for such kind of application. So what kind of material you suggest for transformer at that range of frequency?
Okay, so I will move to this page. Can you see my slide?
Yes.
Okay. Actually, there's so many different companies, they release the different material for the high frequency design. So here you can see for the 1 megahertz design, we have like a 3F45, B40 or P61, ML91. Actually, it's from the different company like ACME, FreshQ, or the Hitachi. They all have a different material for the high frequency design. So when you design, actually, it's not just for the 1 megahertz. Like when you design a 500 kilohertz, you can like look for their data sheet. They will give you some like recommendation for your design.
Okay. Okay. Thank you. The second question. As for the question, my question to the first presenter, before the first presentation, I asked about how he measured his frequency efficiency. He can achieve 98.8%, but I think the measurement technique maybe how to say I don't know about the reliability. How about your measurement of efficiency? How do you achieve 97 point something, and how do you measure that?
Okay. First of all, thanks for your questions. Actually, it's a very good question. I think for that kind of like we do have the measurement here. So we use if you want to ask the machine, we use the Hiroki's power meter measurement. So we use the power meter to measure our conversion efficiency. So that is, I don't know if this answer your question or not, but I mean, but if you want to know more detail, like how do we estimate our loss? The way we did is like for the transformer, that is the most difficult part to estimate. We use the simulation software to estimate the loss in the passive components. Otherwise, the other components like switching devices, we just use simply we will import a real model and estimate, or we can measure the current to estimate the switching loss.
You mean estimate?
Yeah, for the loss analysis. Yeah.
So how do you measure that? I mean, like you use a different individual multimeter, current clamp or something like that?
Yeah, so for this one is the efficiency, we use the power meter. The company is Hiroki. We use that power meter to measure the overall system efficiency. Yeah.
Only one device?
Yeah,
oh, no,
I think
it's
so.
for the system. For the
that's the power analyzer. Yeah, they will analyze the input power and output power and calculate the efficiency for you.
Okay. Yeah. Okay, I see. Because in our lab, we also use a Hiroki power analyzer to do that, but we have to use two different shunt resistor to connect in the input and output side. Then we connect everything to it is so-called the data logger. Then the data logger also calculate everything and export to Excel file.
We did a very similar things, but in our lab for the high current application, we use the whole sensor. We didn't use the shunt resistor.
Sure, it's better. Okay, the next question, sorry, if other has many questions. I have another question. The second part of your presentation by Dr. Chen Chen, he presented about the design of the transformer using many, I think, conventional approaches. My question is, can we apply the same approaches to planar transformer design?
Yeah, I think so. It's the same concept.
So we can apply the same thing because as I know,
so
Dr. Chen Chen, yes, please.
Hi, this is Chen.
Hello.
Hello.
Yes.
Can you repeat the question again?
Please go ahead. I'm listening.
Go ahead. Okay.
My question is, can we apply the same approach to design planar transformer using the approach we use for conventional transformer?
Yes, sure. It's the same. It's the same idea. But if we want to doing the planar transformer, you should consider more like a AC couple loads is more important for the planar transformer design. So we have to choose a suitable core material and design the AC couple loads with the optimized winding arrangement. Okay.
That's all.
Yeah.
Because I'm not I don't have many experience on in planar transformer, but so far as I know, because we work the planar transformer at very high frequency, then we may have to pay attention on the parasitic capacitance in planar transformer rather than the conventional approach, because in the conventional approach the winding arrangement and distribution is different, so and also the frequency is also lower, so we don't have to pay much attention on capacitance, but mainly leakage inductance. But here in planar approach, the leakage inductance is usually very small, but the capacitance is much higher. Is that right?
The interwinding capacitance will much higher. So if you want to, it's like a trade-off. If you want to reduce the couple loads, you should use the interleaf windings, but it cannot prove the capacitance will be decreased. So it's like a trade-off.
So how did you deal with the capacitance? How do you reduce the capacitance? Can you share that?
Oh, for this side, but
okay, so let me explain some more. So for this slide, we didn't show how to reduce the capacitance for the planar transformer design, but I can try to explain very briefly. So there's some like a shielding technology for reduce the parasitic capacitance. So like you can use the shielding to avoid the winding to windings capacitance. So that is one method. But I mean, for the planar transformer, just like you say, we have so many details need to confirm. But the way we propose is like, I think it's the same like a conventional transformer, just in a higher frequency, if you can consider like in this page, if you can consider more like a winding arrangement, like you can reduce the AC loss, or if you can use the interleaf winding, you can also reduce the AC loss. But if you want to reduce the capacitance, maybe you can use like some shielding technology to avoid to reduce the capacitance. So it's kind of like a different way, and it's based on your application and how to solve the problem. Yeah.
Okay, thank you very much.
Okay, thank you very much for the question. So the second is from Dr. Tuấn Đạt Mai. Yeah.
Hello, Dr. Yu-Chen. First of all,
hello.
Thank you for your nice presentations. It's really productive in terms of magnetic designs. So I have mainly two questions. The first of all is about the power density of the quarter turn transformer that you presented in the slide 76. Because actually in my point of view, the efficiency is higher, but the power density of the quarter turn transformers is much lower than the second case. You may move to slide 76.
76.
Oh, 76. Okay. This one?
Maybe the next one. Next one, please.
Next one?
Yeah. When you compare three different transformer design.
Okay, so it should be 70.
Yes, 75. Okay, the previous 75. One, I think so.
This one?
No, the previous one.
Previous one.
On the next one, the slide that you just showed.
There's a little bit delay. Okay, let me try to move. This one?
No, the next one.
It should be 73. 73.
Maybe 73.
73 or?
Yeah, 73, I think.
Okay. Maybe it's a little bit delayed, so I just moved to past the 73. Okay, this one.
No, but let me ask you, because if you compare the power density of the integrated matrix transformer and the quarter-turn transformer, I think the second transformer design has a better power density.
I agree.
Yes. So what brings you interested in the quarter-turn transformer in comparison to the integrated matrix transformer? That's the first question. Yes.
Okay. So thank you for your question. It's very interesting question. So I will show you like for this quarter turns application, just like what you say, because we reduce the turns ratio to 2 to 0.25. And if the magnetic core size, if you want to design the core size is based on the primary winding and the flux density. So if we want to keep the same flux density, of course, we need to use the higher like a core for this kind of design. So I will say for the quarter turn design, the advantage is should be in the for the higher current application. So just like you see right now, because we reduce the turns ratio. So that means we can also reduce the path of the primary winding and the secondary winding. So for this kind of application, the low voltage, high current application, you can see our benefit is higher than the others. So we can get a higher efficiency because we reduce the conduction loss of the winding. So I will say it's based on a different kind of application. For the high voltage application, maybe it's not that good, but if we use this concept for the low voltage one, we can like a more like to prove the advantage of this core structure.
Okay, all right, I got it. Nice.
Yeah.
And secondly, my second question is about the transformer.
Yeah.
I saw that almost of your transformer is the customized one, which are not popular in the market.
Yeah.
So I don't know if you can share about your study regarding to the mechanical strength and the mechanical robustness of the transformer already.
Okay. Yeah. Thanks for your question. Just like you say, it's all a customized design because we have some like a project co-work with the company, so they have some resource can help us to design this code structure. Otherwise, it's very hard to find a company can help you to design this kind of a spatial code structure and especially use their high frequency material. So the reason why we can get this kind of like a new transformer because we have some cooperation with the company, so they help us to build make this transformer.
Okay, thank you so much. That's all from my side.
Thank you very much.
Thank you.
Yeah, so the next will be Quý Tú. Yeah, you can ask your questions.
Yeah, so hello everyone. So thank you for your presentation. It's very interesting. So just a quick introduction from my side. I'm Quý Tú. I'm working for Infineon Technology Vietnam. So so I have some question relating to your presentation. First of all, is can you tell me how is the industry trend of you in using three methods you present here?
Which one?
Also the quarter turn and
this one?
Yes.
Okay.
Yeah.
So sorry, what is your question?
I mean the trend in the current industry.
Okay. You want to know the trend?
Yes.
Okay. So usually
and also and also if you you can have a quick comparison in have you evaluate the cost between these four methods?
Okay. I will try to do my best, but I'm not an industry person, so it's very hard to give you the real price. But I will try to give you the trend of the design. So usually when we design even the PC power supply or the server power supply, the conventional design, the switching frequency is around like a 65 kilohertz to like 120 kilohertz. So based on this kind of frequency, when we design the passive component, you can just like in this page, the first one, static PCB winding, we will use the like a PQ3230 to design our main transformer. And for a resonant converter, we should have an extra resonant inductor in our design. So that is the conventional design. We can get very high efficiency. Actually, honest, I need to say the 97, 98 is not a problem for the single stage. But if we want to like reduce the volume, so what can we do? Even though we have the GaN devices, we can reduce the switching loss from the primary side and the secondary side. But the volume of the passive component is related on the switching frequency, right? So when we increase the switching frequency, we can reduce the inductance or the impedance of the inductor or the capacitor. So that is the whole concept. Like the only way to reduce the volume is try to increase the frequency, because that is the only way to increase the only way to reduce the volume of the passive components. Okay, so the chances, okay, we'll have a new devices. The wide bandgap devices was in these 2 or 3 years is become very popular, and their benefits, they can operate in very high frequency application. So that is the chance we'll try to increase, because we have a new power devices. So we'll try to increase the switching frequency to reduce the overall system volume. Okay, so we will move on. So a lot of people, they just start to do a research about, okay, how to do the high power density converters. So people are more focused on like a integrated matrix transformer or like a planar transformer. So a lot of people, they focus on the planar transformer. Okay, and based on the planar transformer, they will think about, okay, maybe I can integrate the 2 transformer into one, and I can have some idea like a flux cancellation. I can try to reduce the core loss, or I can try to reduce the AC loss based on a different like a widening arrangement. Okay, so here's a chance we'll try to like move to a high frequency design. So if you want to ask what is the price and what is the like compare with the conventional way, I will say that like when people they did this kind of like design, they will think about they can save some money, because for this kind of conventional design, we need to spend a lot of people to do like a soldering, like to make the circuit. But for this kind of like a circuit design, it's very easy to manufacturing. Actually, it can be an auto manufacturing, because it's very simple. I don't need too many people can build up the power supply. Okay, so that is another concept and idea. So if we design a panel like this kind of high frequency DC to DC module, and I can save the people, and I can make the product more easily by less people. Okay, so I think that is a chance of the switching power supply from the low frequency to the high frequency.
I would like to add the additional point for the cost of the high frequency power converter. So firstly, I think it's about the passive component. Like with the low frequency, you have to use a lot of electrolytic capacitor, and it's not reliable, and the cost of electrolytic capacitor is quite high. And if we can count like the quantity of million products like this, so in this case, the cost of the device, even the GaN device EPC, the quantity of million, so the cost of this device is quite small. It's less than $1. It's quite small. And for the PCB, yeah, if we should do a research, the PCB layout is quite like expensive. But if we just consider for the industry, the quantity of million, the PCB cost is also like is minor. That's why like people, they want to go higher frequency to reduce the cost and also reduce the volume, because like most of the power supply server now, the power converter only like occupy a very small room in the system. Yeah, that's my point. Thank you.
Yeah, thank you.
Thank you.
Yeah, thank you. So, yeah, I have one more question regarding to the design for manufacturing, right? regarding to LLC converter, so consider I guess the leakage inductance is also the tolerance of leakage inductance is also one important requirement. So how is with the two proposed methods, how the leakage inductance can be controlled? Yeah.
Okay, so you mean this idea?
Yes, this idea and compared to the quarter.
Oh, okay.
Yeah.
Oh, so for the quarter turns, actually, it's very hard to control the leakage inductors because the main purpose is like we will try to reduce the conductive path. So we will not try to control the leakage inductor. So for when you design the quarter turns, actually the leakage inductor usually is very small because we use the interleave widening, like a widening arrangement. So that means we will get very small leakage inductors. So it's a little bit different concept for the different like magnetic design. So for the quarter turns, we will say the leakage inductor will be very small. So if you want to operate in the like a resonant frequency, you need to control the output resonant capacitor to make your circuit operated in a resonant frequency. Yeah. So did I answer your question?
Yes, yes, understood. So just regarding to the tolerance of for the manufacturing, right? So which one, for example, the conventional methods with the BCB one. So I think the industry guy they already have their method for controlling the tolerance. But I just wonder whether in our proposed methods, so we already think about the control the tolerance of the leaky inductance in
Yeah, I think that is but I mean, if we use the conventional transformer, I will say the tolerance is higher than the planar transformer because when you design the planar transformer, you use the PCB to be your widening. So all the effect will be very similar. But if you use the handmade transformer, like a lace wire widening, like it's made by people, right? So your tolerance will be higher than the planar transformer. So when you use the planar transformer, the core size and the PCB will limit your tolerance, will make your tolerance smaller than the conventional lace wire handmade transformer.
Okay, yeah, thank you.
Welcome.
Yeah. So I think it's about time to have the last question. So the last question is from Mr. Tất Thắng Lê. Yes, can you raise question here?
Yeah, hello, Professor Yu-Chen Liu. I'm Thang from Seoul Tech in Korea. And I have a question related to some unbalance because of now we as you saw in this converter is planar transformer. That's considering some it look like the so many converter in secondary side. So I think that have some unbalanced problem that you especially in the voltage unbalance because of now the current maybe you connect in the series, so that has no problem in the currents unbalance. But in the voltage, did you consider did you simulation or in your experiment result, did you see some unbalance in the voltage between the each module?
Okay. Oh, thanks for your question. It's a very good question and it's very important. Okay. So the way we did is like we will use the pre-simulation to verify the current is balanced or not. Just like in the page 70 you see it right now, we use the Maxwell to make sure all the conductive paths is equal. So from our simulation, we can see all the current is balanced for each leg. But in our some like a spatial case, we'll try to make the conductive path is not equal. So you can see the output voltage and current is not balanced. So because it's in a real circuit, we use the devices we use is very hard to make sure the current. So the way we did is that we will use the thermal image to detect the thermal at each devices to see if we have like a current unbalancing. It should have the like a very hard part, the hard part you can see on each devices. So that is the way we did, like before we made the circuit, we will simulated the circuit has the current sharing or not. If it's not, we'll try to improve our layout to make it become more like a symmetric.
Yes, thank you for your answer. But my mean is about the voltage unbalance. Maybe the current is not is balanced because you connect in series. But in the voltage, how about the voltage? How we can confirm about the voltage unbalance between leakage?
Okay.
Yes.
Because the voltage is in parallel.
Yeah. Sorry. Yes. Okay.
Yeah. So the voltage should be in balance.
Yes. Okay.
Yeah.
Okay. I see. Yeah. Thanks.
Thank you.
Thank you.
Yeah, thank you very much. Yeah, so it's time to give the stage to the chair.
Okay, thank you very much, everyone, for participating the today webinar. Actually, Professor Liu is not a stranger to VPEC because he presented a distinguished lecture in last year, December, right?
Yeah.
Then maybe some of you here attended that lecture before. Then once again, thank you very much for coming today, Professor Liu or Professor Stephen. Yeah, it's very nice presentation.
Thank you. And thank you for your guys' invite. And I really hope the VPEC can be more stronger in the, you will be a very stronger in the future, I believe, based on your leadership. I mean, that is for sure. And just let us know what can we do and help, and we will do our best.
Yeah, thank you very much. Actually, we are looking forward to receiving the help from you. Like if you have any like scholarship or like a open position, you can share with us. And if we have any like good candidate, I can recommend to you. And then the first one, okay. And then the second one, as I showed before, we are now organizing a conference, international symposium on power energy and cybernetics. So if you are interested in our conference, so you are invited to submit as many as possible, short paper or long paper. Okay. Actually, this is the first time we organize the conference, so we cannot make sure about the index of the paper or like the original paper. But if you can submit or share your short letter, 2 pages, and you can already presented the paper before in any conference, but you can share once more with us again in our symposium. It will be also very great. We are now preparing for the release of the conference paper. Then after the release, after the announcement, I will send you the invitation later.
No problem, no problem.
Okay.
I will do my best. And once again, I need to thank the Dr. Chen. He's spent a lot of time and effort on this talk. So yeah, in the future, and it's very welcome to invite him to give also like a support this community.
Yeah, sure. I also sent the invitation to him as well.
Okay.
Okay, so this brings us to the end of the webinar today. So could you open your camera, then we can take a group picture?
Oh, sure.
Yeah, and can you turn off the share screen, please?
Oh, yeah.
Okay. So everyone, can you open the camera?
Pretty cool.
Okay, so today is very tough to my co-chair, Dr. Zoom. It's now maybe 5 a.m. in the US, right?
Yeah, it's right. It's about 5:30 a.m. here.
5:30. Oh. Okay, so I will take the print screen. Others, can you open your camera, please? Other participants? Okay, so I will take the print screen. Okay, so smile. Okay, I take many. Okay, thank you very much. This is the end of the today webinar. So see you in the next event. We organize this webinar every month. So next time, if you have time, especially Professor Liu and Dr. Chen, if you have time, you are welcome to join us in the next month's webinar.
Okay, no problem.